When we talk about the signature analysis, we're going to be using a digital storage scope like you see here. Let's take 1 minute to talk about the setup on this digital storage scope. Across the bottom, you see 1 second. That means we're looking at 1 second per division, and in all of our scopes, we're going to have 1 second. In this particular case, it's a 5-second window. You'll see others where it's 10 seconds on different models of scopes. But each individual little square, represented by those 4 vertical lines, represents 1 second. On other systems, you will see 10 vertical lines, representing 10 seconds. But each one is going to show the same picture. 1 second per square. Now, going vertically, we go from 0 at the bottom to 1 volt at the top. That means each one of those 3 horizontal lines represents about 0.25 volts, with the middle one being a half a volt. What you see about this pattern is it's moving smoothly about the 0.5 volt bias. Now we know the stoichiometric is 0.45 volts, so we can say that this pattern is moving evenly above and below stoichiometric. And we got to go back and remember this relates back to the chart we were using earlier. But one of the things we'll be doing is we'll be looking at speed. Now speed here is normal activity, where we're going from lean at the bottom to rich at the top. Remember, our AFR chart said when the voltage is high, minimum 0.85 volts, we're rich. When it's below 0.45, down to a minimum of 0.1 volts, we're lean. Now, during normal activity, we don't expect to see 0.1 and 0.85. We do expect to see, when we snap accelerate, go over 0.85 up, and we deaccelerate or slow down, go below 1/10 on the bottom. That's called our speed test. The PCM is really going to go into a specialized mode where it's going to switch rapidly from lean to rich and measure lean to rich switch time. Then it's going to switch rapidly from rich to lean and measure rich to lean switch time. We're going to show you how to do this for your own test. But its speed is between 2 set points, a high and a low, or a low and a high. Reaction time is the time it takes to change the signal which has been heading lean to start heading rich, and vice versa. A signal that's been heading rich, turning and going lean. Now we must define the rich point. In our AFR charts, we said that the minimum rich, when we go full rich, must be at least 0.85 volts. But this can be anywhere from 0.85 volts and to 1.2 volts and still be normal. So what mode 6 has to do is it has to determine what is this rich point at this life on this oxygen sensor, so I can measure speed between rich and other points. Then it's going to do the same thing for lean. We said that in the AFR chart it must go below 1/10 of a volt. It can go as low on some vehicles as minus 0.075 volts. That's 75 millivolts minus. Some vehicles don't like minus values at all. You must be vehicle specific. But we need to know what this point is at this life. If we're going to measure the time switching from rich to lean and lean to rich, we need to know what those 2 points are. Mode 6 is going to tell you that. If you're not able to utilize a scope like this, utilize mode 6, but understand from this picture what it's telling you. Now, the switch ratio most commonly refers to the activity of the post-catalyst and pre-catalyst sensors. But we can also be looking at switch ratios rich to lean, lean to rich. We're either going to compare for another sensor or different phases of the sensor. And then the heater operation, the most common method is time to activity, but you're going to see some that's actually going to measure the resistance in ohms in mode 6, and you're going to see some that's using amps in mode 6. Others use time to activity. How long does it take it to get into closed loop? Now, let's talk about what they're actually measuring and just restate what we're looking at. The oxygen sensors are placed in the exhaust stream to measure oxygen not burned during the combustion process. Now we know if we have a misfire, we send unburned oxygen and we send hydrocarbons. And while the oxygen sensor reacts with hydrocarbons and CO to measure oxygen, it does not actually measure CO or oxygen. It's measuring the unburned fuel. The whole premise of our air fuel chart is based on the voltage relating to oxygen and air fuel ratios. This particular vehicle we looked at here has three O2 sensors. One right by the manifold, which is a pre-cat, one right before the catalyst, which is pre-cat, and one after the catalyst. We do this for catalyst efficiency testing, and we're going to show you an absolute valid catalyst efficiency test. But before we do any of these things, before you test anything, you must make sure we have normal fuel control. That means if long-term fuel trim is within plus or minus 25%, you can continue diagnosing. Now that's the official number. Our number we use personally is 15 to 20%, depending on the age and mileage of the vehicle. Fairly new vehicle, we want to see it within 15%. Older vehicle, we'll give it 20. Ideally, before we return it to the customer, we want to get it below 10% correction. This means something has been going wrong with fuel delivery or fuel control that has utilized the oxygen sensors to correct for it. So don't get too far down the road before you fix fuel control and fuel delivery. Now, one of the things we're also going to use to look at this, we can look at it with a scan tool. This is a 302-second recording we made looking at this particular oxygen sensor. It looks very much like the pattern we had before. So this is a good starting point. Now we're going to get down very specific and talk about the patterns. Now once we have ascertained we have normal fuel control, we start judging our rich and lean. Now typically we see it oscillating between 0.2 and 0.8 volts. Very much like you see happening here. The oxygen sensor can also be graphed on a DSO. This one has 10 seconds across. The last one you saw had 5. But look, it's still 1 second per division. It's still 0 to 1 volt. Even though we put our 0 in the center of this large screen, we're going between 0 and 1 volt. So while different oscilloscopes have slightly different arrangements, look at the pattern. It's showing us the same thing. Now, how do we connect it? We're going to hook our our positive lead into the signal. This is the right upstream O2 signal on this particular vehicle. It's pin number 4 on the O2 sensor. It could be pin 60 on the PCM for this particular vehicle. So that's our positive lead. Our negative lead, we're going to show this going to ground. Now, the most convenient ground everyone picks is chassis ground. But for oxygen sensors, let's talk about that. It's not necessarily the best ground because this particular vehicle, the PCM is controlling ignition and fuel injectors, and we have a lot of currents switching off and on at this particular ground. We'd be much better off looking just below the red lead at pin 91 on the PCM or on pin 3 of the O2 sensor and getting sensor ground. It has less noise. You can use either one, but you will get more noise and hash if you go here, which is the common place people connect. Here is a perfect pattern. Again, we're back to 5 seconds on a screen. The pattern is the same, 0 to 1 volt. It's switching back and forth in a balanced manner. That means we have good fuel control, and we're going to really talk more about that when we get the catalytic converters. When we speed it up, we can speed up the whole process. We can control faster. It switches much faster. Now, when you come to switching speed, this is where switching speed becomes important. Look how straight up these lines go. When you have a slow oxygen sensor, it won't be able to keep up at this higher speed. That's why oxygen sensor switching speed has become so important of an issue. So we've defined our rich and our lean. The minimum voltage The minimum range, the smallest range it can cover, is 0.1 volt to 0.85 volts. Rich has got to be at least 0.85 volts. That's when we snap accelerate, add enrichment, drive the system rich, go wide open throttle on the highway. We want to see 0.85 volts minimum. If not, you've got a bad O2 sensor. When we take it lean, we snap accelerate and then let it decelerate for a moment. We want to see it go below 1/10. You'll find these values listed as the max and min voltages in mode 6. So when you use mode 6, you are in effect doing a pattern interpretation. We would have to use a lab scope to verify any other way. When we look at the total range, it's 1.2 volts max, and that's only on certain cars, and 80 millivolts minus, that's minus 0.075 millivolts, or 0.7075, which is 75 millivolts. So we want to see very little lean. It almost has to stop perfectly at the zero line. You will not be able to see millivolts very easily. So you've got to be careful you don't go well below 0 volts. Now let's talk about switch points. One of the things you're going to hear and see all through O2 characteristics in mode 6 is switch points. This is the ideal rich switch point for a particular vehicle we're working on. It's set at 0.6 volts. Now what is a switch point? A switch point is the spot where we start changing. What we have been doing, getting as the voltage has been coming up, we have been stretching injector pulse width. Short-term fuel trim has been asking for more fuel. When we get to 0.6 volts, short-term starts asking for less fuel. As a result, we see the turn and the system starts down toward the lean side. We get up to the top of this, we're going to be near 14.5 volts if the oxygen sensor has the proper speed. If it's a slow oxygen sensor, we can be going richer than 14.5, all depending how slow the oxygen sensor is. The lean switch point, which is near 14.8 to 1 air-fuel ratio, on this particular vehicle is at 0.3 of a volt. When this signal reaches 0.3 of a volt, the short-term fuel trim is going to start adding fuel to turn it back toward the rich side. Now, we need those 2 points because that tells us things about reaction time. If reaction time is bad, we have to start that sooner. The voltage will be lower at the rich switch point and higher for the lean switch point. This comes from our secondary fuel trim. We start making changes to make this react properly. So we've got 2 switch points. Now, the time between switch points is measured in mode 6. You will see things referring rich to lean switch time between rich to lean switch points and lean and rich to lean switch points. In this case, we're going down from rich toward lean. This is the lean to rich switch point. If we're going the opposite direction, coming from lean going to rich, this is the time between the lean to rich switch point. Nice to know how balanced these numbers are. If you have a great deal of imbalance between lean to rich and rich to lean, it means it's biased in one direction or the other. And you're probably going to find long-term fuel trim is up higher than we want to have it before we deliver it back to the customer. Remember, delivering it back to the customer is quite a bit different criteria than saying plus or minus 25% before we can even start this test. Big slope is a measurement Chrysler does, which is measuring the volts per millisecond between the rich points. It's the rate of change, time per volt, volts per time. You're going to have them from between the lean switch point and the rich switch point. Now, what is the minimum lean voltage? This is a value we need to know if we're going to do some other testing. It's got to be below 0.1 volt, remember? Then the max rich volt, it must be above 0.85. Again, if you cannot use a lab scope like this, rely on mode 6. Look at the max rich, max lean values when they're listed. This tells you how far you're going each direction. The PCM is reading this scope pattern for you. Utilize it if you have trouble using a scope pattern. Now the PCM is going to use statistical averages to look at long-term shifts. It's going to modify some of our switch points based on these long-term shifts. Exponentially weighted moving average is one processing technique using statistical data to determine a new average. It retains part of the old information, brings the new in gradually to make gradual changes. That's the difference in this versus just a plain average. But the PCM is going to store this new average and keep alive memory and use it for pass and fail criteria and for adding into future moving averages. If the DTCs are cleared, the exponentially weighted moving average should also be zeroed out. We found some cases in earlier years where that did not happen, so be aware of that. At that point, you'll be dealing with uncorrected condition that caused the shift. So if you clear codes or zero it out, then you can look at what condition caused the problem. One of the things we frequently do is we clear out everything and see where we are when nothing has been corrected. That'll help you spot problems you may see covered up by long-term fuel trims and the exponentially weighted moving average. The oxygen sensor under these conditions may not be normal. It may be stuck rich, stuck lean, because once you've cleared the DTCs and you clear the moving averages, you're going to be looking at raw data. That's a good thing to look at. But let's talk more about these moving averages. It's important because fuel delivery and control components deteriorate over time. It's an advanced version of the adaptive learning. The oxygen sensor reports to the PCM shifts long-term short trim to correct for long-term corrections. Then it stores it in memory. Exponentially weighted moving averages simply takes this correction a step further and under a slightly different level and utilizes more of the information from the post-catalyst O2 sensor. So we're going to start testing our O2 sensors. But I want you to look at something here on this lab scope. First, we're going to identify a few things. We're looking on the green scale at 1 volt signal. As soon as we start testing, we find out very quickly we need to pay attention to what's going on. Now, I want to talk about the scales. Look on the left side of this. The blue writing is for the amperage. Our blue trace is between 0 and 2. That's just slightly above 1 amp. Our green trace uses the green numbers. It's between 1 and 2 volts. Notice the scale goes from -3 to +5. Why are we reading so high? This reads 1.5 voltage. Is this a problem or is this normal? We want you to consider all that, and we keep stressing using manufacturing specific information. Here's another pattern that looks like it's wrong. On the left, we see that we're on a -5 to +5 volt scale. That means the middle of the screen, right by the big V, is 0 volts. So this pattern is going between 0 and about 3.3 volts. That definitely violates everything we said we're going to see on these cars. So you pay attention. When the scale is different, and it has to be different to work on this car. This particular vehicle happens to be a next generation controller O2 signal from Chrysler. You're going to see different values than you saw before. In fact, when you hook your lab scope up, your values are going to change slightly anyway. You're going to have to really use scan data to really evaluate both of these, and we'll show you why later on. Notice here, this is a JTEC, Jeep truck engine controller, where we have a separate engine controller and transmission controller. It started off above 1 volt, and as it warms up, it moves on down, and then pretty soon it goes into closed loop and starts looking like a normal oxygen sensor. So be aware of these differences. But once we start looking at this, and we eliminate JTEC before it warms up, we eliminate next generation controller at Chrysler, Ford, GM, Chrysler begins to look the same. Stoichiometric is going to be in the middle. Now notice here we start at 0 in the middle and go to 1 volt on our green scale. Stoichiometric is in the middle. That's the ideal point, the point we talked about on that graph. We have switch points, high and low, and we're going to define all of this. But we're going to say it one more time just to remind you. Do you have good fuel control? Is short-term in range? Because we're going to show you some cases with scope patterns where it's not. We're going to show you why. Here is poor fuel control. Let's talk about the voltages. This signal is ranging between 0.4 and 0.55 volts. It's the same 10 seconds we've been looking at. We got 1 second provision, we got 10 seconds. This is not in fuel control. Now, question is it the sensor? Is it fuel control? Or is it fuel delivery? Remember, we divide fuel control into the mathematics we do based on mass airflow and everything else to compute injector pulse width. Fuel delivery is putting fuel reliably to that injector so that you get the right amount of fuel for that pulse width. If the pressure's wrong, the volume's wrong, the injector's dirty, we've got a problem. Well, what about the O2 sensor? Well, what's going to happen? The way the computer is going to handle this is during the process, the PCM is going to shift the air-fuel rich and lean to test for O2 operation, get the max and mins. We're going to do the same test, only we're going to use throttle changes. Now, operating speed. O2 sensor speed isn't recorded because the PCM determines if fuel was delivered for acceleration. How can it tell if it's slow? It can determine if fuel was shut off for deceleration. If it's slow, it loses that information. The PCM can keep air-fuel ratio correct doing steady throttle to reduce emissions. All of these are only possible with proper speed of the O2 sensor. The O2 speed is one of the most overlooked part of sensor testing, and unfortunately we cannot tell you any way to do it other than using a lab scope. Now, Ford's Mode 6 calls it an amplitude test. And we're going to explain this rather complex thing here. We've drawn a line at 0.5 volts. What Ford does is go from lean to rich very quickly. And in this blue box is the time they start the test to the time they end the test. The left side's when the test starts, the right side's when it ends. A is a sensor that's very fast. It goes out of the box at about 0.6 of a volt. B goes out of the box at about 0.4 volts. C goes out at 0.1 volts. C is a very slow sensor. Now remember, fuel has changed. We've gone from lean to rich. The question is, how long does it take the oxygen sensor to see that change? Let me say that one more time. We've gone from lean to rich. How long does it take the oxygen sensor to see that change? A sees it right away. It's a brand new sensor. B doesn't see it for a while. It takes it an extra second or two, about 1.5 seconds, before it reaches the same point. And C is a real bad cat. He hardly ever makes it. He never really catches on. We've already changed and gone somewhere else before C catches up. And if we're in normal high-speed fuel control, we're going from rich to lean before B even catches up to the rich side. That's why we fail so many oxygen sensors in IM240. It's the #1 failure
If you combine all the oxygen sensor failures into one failure, they outpace everything else in California, Wisconsin, Massachusetts, Indiana, anywhere you want to go. The O2 sensor is the #1 cause of service codes on OBD2 cars. Wow. Let's look some more at this. How do we do this test? Now we're taking our same scope pattern and we captured one. We let the pattern go down to the lean side, and then we snap the throttle open, and you see the change start at the bottom, and you see it end at the top. We want to see nice straight patterns. Does that look like the A pattern we just showed you? This is the way we duplicate it. So if mode 6 or trouble code says you have slow O2, this test can verify it. If you have no fuel control, we got to start testing. Oxygen sensor, fuel control, fuel delivery. Let's start with the O2 sensor. Snap the throttle wide open to see if the O2 sensor responds. What should happen? Well, first of all, we're going to get enrichment and go full rich. If we can respond quickly, go to fuel control. Is the calculation right? Go to fuel delivery. Can you deliver the fuel to the injector when it's open the proper amount? Or do you have to add a bunch of long-term fuel trim in to overcome low fuel pressure, dirty fuel filters, weak fuel pump, dirty fuel injectors? Do you have to add fuel in to overcome mass airflows that are dirty? Or any other of the sensors that are critical to fuel control? If the sensor doesn't respond, it's easy. Change the sensor. Now, this may seem like a real dumb thing, but we find a lot of people going in the ditch here. If we can't get good fuel control and good delivery, we need to replace it. And we've divided the sensor from the rest of the system by doing this test. O2 heater operation. If the oxygen sensor doesn't go into normal operation soon enough, test its heater circuits. You may also have a code and information in mode 6 telling you about that. Either way, we're going to see what we have to do to test it. Our method of testing it is to use a low amp current probe. As you can see here, we're looking at a purple and white wire and showing you where it is on the actual oxygen sensor itself. We're going to clamp around that wire. We can either use the positive side or we can use the ground side here. But if you want to capture the maximum current flow, the engine should be cooled. We're going to read the amperage and measure the O2's heater current. Now the question is this 2.5 amps normal, high, or low? Well, first of all, you need to know something. Just take Ford as an example. Ford has 4 different heater current specifications for a very narrow range of vehicles. We know Chrysler's got a dozen or more. The real message is, when you have available, use mode 6 to tell you what the specification should be. You can look at the max and minimum limit information to see if this is normal or not. In our book, it's slightly higher than normal, which is going to take us directly to the O2 sensor itself. But if it's lower than normal, we're going to have to do some circuit testing before we condemn the sensor. First, we're going to check for B+ at the heater. Here we're looking at 12.8 volts, which is what's battery voltage. We put our voltmeter on pin 1. Our voltmeter on pin 1 and our ground lead on engine ground, battery negative. And we're also going to check the ground circuit. Now, the first indication, anybody that knows us know that we like to see 50 millivolts in ground. This is 321 millivolts. But look just above the voltmeter to the right, and it says that ground has duty cycle control. So that may look like a bad voltage. That's why we use current flow. Now, the heater operation changes between manufacturers. Vehicle-specific information is important because there are major differences. I'm going to show you using Chrysler between S-Spec, Next Generation Controller, and JTEC, Jeep Truck Engine Controller. Now, here is a GM heater warming up. As you notice, we first started to turn it on. Going to our scope, we are on a 1 second per division, half second per division, 5 seconds across the screen. The green scale on the left is 0 to 10 amps. We're looking at around 1 amp, a little less than 1 amp, about a half amp. Yeah, let's blow it up so we can see it. Now we're looking at, you can see well less than a half an amp. This is normal for a restart, but we've got a couple blips in the middle. We need to understand what those are. We'll talk about it. If you have no current flow, go check the fuse. But this is normal activity. And looking at this normal activity, we see that it's being turned off by the PCM. What the PCM is doing, current flow goes to 0 when PCM ungrounds the control for the ground. That's why ground voltage is higher than normal. Not all vehicles have that. If you have a problem where you can't get a good current flow, check for normal grounds. You have to have good grounds in order for them to draw full current flow. Early crisis systems ran the heater current test after 6 to 12 minutes after engine shutdown. Now, you could watch the monitor if you could ever catch it running. We tried for years and never could catch it running. But why wait so long? Why waste time? We can run our own test. Here is an S-spec, and we're going to break each one of these signals down. Right here in this red box is our startup. We've gone on the left of the red box. The key is off. We start the engine, start it running, and start recording the information on the right. Now the green relates to the green on the far left scale. We have 0 volts at the bottom, 14 volts at the top. It's 14 volts. This is ground control. When we remove the ground, we go to battery voltage. When we supply the ground, we go to 0 volts. So that's normal activity right after startup. Lots of activity, limiting current flow. Battery voltage comes up, stays at 14 volts once the car gets started into steady. But look at the current flow at the bottom. It's varying from 1 amp to 0 amps. Notice the little black arrow. When the ground is supplied, we have 1 amp of current flow. But notice what happens after the car's been running for a while. We turn ground control off and give it a ground all the time. We see here running a steady current flow. It indicates a good sensor. The lack of duty cycle at startup would indicate to you that you have something wrong, because you should be limiting current flow on a cold sensor. Limiting current flow is not needed once the heater element heats up. Here it is on a JTEC. Start the car up, starts running. As soon as the car starts up, starts running, we turn the heater current on, and it just starts going downhill slightly. If you look very carefully, we magnified it here. You can see we start off at about 1.8 amps of current flow, and then it tails off. That's normal activity. Here we turn the key on, started the car, and it tailed off. This is normal activity. We can see what's going on there. In this particular case, this is a Ford. The current settled down at about 1.06 amps, or about 1 amp. Did not need any duty cycling. So you'll have some this duty cycle, some that are not. Some vehicles, like JTEC, have a special operating mode to identify heating failures. They have a 5-volt pull-up, like here on the left. The pull-up resistor will drop down to below 1 volts when the heater warms up, when the O2 warms up from the heater. The resistance of the element in an O2 sensor drops drastically as it warms up. It's using that capability. Now on the right we have S-spec. It's very much like most vehicles, 0.45 volt pull-up. But here's something you need to be aware of. We have our scan tool here. The red arrow now is pointing to the voltage on the right, and the spot on the left where the little dotted line is reading the voltage. We have a DSO connected. This digital storage scope is connected. A digital storage scope is only 1 mega ohm input resistance. It can cause readings to be lower than normal. It will pull the voltage down slightly, particularly in high resistance circuits like this one. When we disconnect it, the voltage goes to 4.76. So if you really want to measure this voltage, you need to do it with a scan tool. And if you have a generic scan tool, you're going to see 1 volt for a long time. We got the big red arrow saying it's off scale. till it warms up enough that it drops below 1 volt, you're going to see nothing but 1 volt data. Now, we try to tell you, the oxygen sensor is going to have good fuel control to work properly. The heater's got to be working to warm up quickly. And we showed you how to check fuel control, the heater, and everything else. When you have no fuel control, you have a problem. So we're coming full circle, coming back to remind you again to go back and make sure you have good fuel control before you rely too heavily